Well, I'll say good morning to everyone. So I have one more class this semester I'm going to have to miss. And unfortunately, that's the class next Tuesday. And so we're going to record Tuesday's class tomorrow morning at 11 o'clock in the room next door. So if anyone's available, you can come and see an early version of the next class. Okay, so we were talking about, question?
I was just wondering, there's a homework due that day?
Oh, the homework's due. Let's make the homework then due on Thursday. Thursday next week then. That's a good point. The other thing about the exam, I didn't comment. Some of you did very well and some didn't do so well. And but if you didn't do well, hopefully, I mean, you can do well in the final exam, and I'll tend to forget the first exam in that case. At the beginning of the semester, I gave you a formula of how the grade is determined, but I always look at the final exam, and if you really know the material much better than you did on the earlier exam, I'll give you the benefit of the doubt. Of course, at the same time, I guess if you did well on the first exam and you do bad on the final exam, you won't. You'll do well on the final exam too. Okay. So we're talking about looking at spherical surfaces, and the first part was measuring the radius of curvature, and we said one way of doing that was to use a spherometer, and we had this expression here for the if we had a spherometer with three balls that were separated by a distance d, and the radius of the three balls were each r, then we had that capital R, the radius of curvature of the unknown surface, was d squared over 6h, where h is the sag, basically. D squared over 6h plus h over 2 plus or minus r, where we have the positive sign if it's concave and the negative sign if it's convex. And I want to just go through a short derivation of this expression here. It's not too difficult. Let's show it here. And so we're saying that we have the three balls here at the corners of this triangle, and they're separated by d. And I'm going to draw a line here, halfway up here, bisecting this angle, because we're going to put a little plunger here that's going to go down and touch the surface. And so we'll say that's a distance A, and since that angle is 60 degrees and we're bisecting it, this must be 30 degrees. And we go halfway across here, that would be d over 2. And so we'd have here the cosine of 30 degrees is d over 2 divided by A. And so we could solve for A. And A turns out simply to be d over square root of 3. So just looking at it sideways, here are two of the balls. And if we say, well, this surface has a radius of curvature of r, so we go up here r away. And we come down here, and these are the balls. And so if this is a distance r from the surface, it's a distance capital R minus little r from the center of the ball. Now, if I have a flat surface here, I'm going to define h, the sag here. I mean, h is going to be 0 for a flat surface. So that would go straight across here. And so if I draw a line between the centers of the two balls here, and I look at how far it is from there down to the surface, that is r plus h. Now, those of you who have downloaded this before last Sunday, I think it is, you may just have an h there or something. Anyway, I found I had a small mistake, and I corrected it on Sunday, posted a new version up there. So this is r plus h. This distance here is d over square root of 3. And so this distance down here is r, capital R minus little r minus h. And so we can just go that capital R minus little r squared is equal to capital R minus little r minus h squared plus this distance here, d over square root of 3 squared. And we square this out and solve for r. And we're going to get that r is d squared over 6h plus h over 2 plus r for a concave surface like this. Okay. If this is a convex surface, so now I'm still measuring from up here, so the balls are outside here. And so we would have a similar expression here, except now instead of a r minus, capital R minus little r, in this case it would be capital R plus little r. And so if that's a convex surface we're measuring here, then this becomes a minus r. Concave is plus r. So those of you who have used the spherometer in a lab, and you had the old-fashioned one, you didn't have the electronic one. Is that right? Because I don't know if we have an electronic one in our lab. You didn't actually go through this calculation, I don't think. You probably had a book you looked up the numbers in. Yeah. And but the book had two sets of tables. You had one for concave surfaces and one for convex surfaces. And that's the difference right there. Okay? So that's probably the most common spherometer is one where you have the three balls in a triangle, like the equilateral triangle like this. If the balls are in a triangle with sides D1, D2, D3, and to tell you the truth, I've never seen a spherometer like this, but if you have one like that, then it turns out this is the equation relating the D's and the H and the R's and to the radius of curvature we're measuring. And I'm not going to derive that expression here. Okay. Another spherometer you see sometimes is just a ring spherometer. And the ring is kind of sharp on one side, and so that just sits on your surface. No balls in place. And this would be the expression for that, where R is different in this case. R is the radius of the spherometer. And I might as well just go through a very short derivation of that. So we just have this ring we're sitting down on the surface, and R is the radius here. And this is capital R, the radius of what we're measuring. And then this is, of course, R minus H, the sag here. And so just capital R squared is little r squared plus R minus H, quantity squared. And you go through here and simply solve for the radius of curvature of what you're measuring here is little r squared over 2h plus h over 2. These are not as common, at least in my experience, have not been as common as the ball one here. A few comments about the spherometer. What's the major source of error in doing a measurement? And it's really determining the exact point when you're turning a micrometer or whatever, and you're moving this ball up and down, and when do you really just touch the surface? And that's probably the major source of inaccuracy here. And I've read many places that in some spherometers you look at a Newton's rings pattern when you're coming down to touch it. It's I guess a little transparent ball, and you look for the Newton's ring interference pattern. And I have to say, in all my years of using spherometers, I've never seen one that actually worked this way, but all the books say they exist. I've never seen one at a trade show either, but I'll take their word for it. They probably do exist or have existed at one point. So that's essentially everything I wanted to say about a spherometer. And let's go on to another way. The autostigmatic measurement. I'll come back to this page, but let's just look at a diagram here. So what we're doing, we have some type of traveling microscope here. And we're looking into where we focus on the surface. And then we move this back here to where, so the light, some light coming in here focused, we're seeing when it's focused on the surface. Light coming in here, when this is at the center of curvature, it's going to be focused right back on itself again. And we could observe that with our eye here. And so there's some type of scale here where we're going to measure just how far we move this. And it might be an encoder, or it could be an interferometer, where we're essentially counting fringes as we move from this position back to this position here. And this is a common lab experiment. Have you ever done a lab experiment doing this? Yeah. Okay. And let's see, I had a few more words here, but I think probably I've said everything that's on there. So you focus on the surface, you get an image of the source, and then you go back to the center of curvature and see it again. So this is fairly commonly used, and you can certainly see how to do it for a concave surface. But let's say I want to measure the radius of curvature of a convex surface. How could I do that? Well, you could look in the next slide, or you could think for a second here, I guess. Well, the trick you always do is you add another lens to the system. And so I can put in another lens here, and here's my traveling microscope, and I'll just use this positive lens to focus the source here onto the surface, and convex in this case. And then I'll move this up here to where this coming in here is normal to the surface. And again, the distance I move is gives you the radius of curvature here. So we have to have something, another lens here, that produces an image here farther away from the lens than whatever the radius of curvature of this convex surface is. And that's the only requirement. So you just have to add the additional lens, and you don't need to know the focal length of this lens or anything. You just need to know that the distance to the image here is greater than the radius of curvature of the surface. So that's commonly used. Now, of course, if I were going to do this, I would use an interferometer, and the same, exact same idea, but what we're doing here, we're looking at interference fringes. So this could be a Fizeau interferometer, it could be a Twyman-Green interferometer, whatever. But I'll set this up here so we get a null fringe, and then we'll simply move this along here till we're focused on the surface and get another null fringe. And again, the distance we move gives us a radius of curvature. And in some interferometers, it will be set up, and so even if you don't have a perfect null fringe here, the interferometer will measure what little curvature you have left and can compensate for that in doing the measurement. So you don't have to be quite so precise at getting this exactly at the null. And I know back in my Wyco days, we sold a lot of these radius slides like this. This is such a common way of measuring radius of curvature. And probably the most common ones were probably 2 meter long. So this would be a scale here with an encoder on it. And so you could measure radius of curvatures up to 2 meters. And you could measure to, I don't know, a micron or maybe even a fraction of a micron of whatever the radius is. Okay, any questions? So we had spherometers, we had radius slides, and the last one here is Newton's rings. And you're all, is anyone here who's not an expert on Newton's rings? I didn't think so. No. Good. Well, I'll still say a couple words here. So, I mean, if you're measuring something that is not a very short radius of curvature, you simply would put that surface next to your flat, and you look at the interference fringes, and you know that, oh, let me think here. What does in going from one fringe to the next, the OPD changes by a wavelength, always. And if we're looking at this, pretty much normal incidence. So the separation between the two surfaces would change by half a wavelength. And we know that for something that's not, that's a pretty long radius of curvature, we know that the sag goes as what? Rho squared over 2r, rho being the distance here, and r being the radius of curvature. And so we'd have rho squared over 2r. If we're looking at the number of fringes, why did I draw a dark fringe in the center? Is that right, or did I just make a mistake? Yeah. So you would have a phase change on reflection, different from the high index to the low than what you have low to high. So if these are really in contact here in the center, it would be a dark fringe in the center. So if I go out to the mth fringe from here, then we'd have rho squared over 2r is m lambda over 2. And so then you can simply solve that r is rho squared over m lambda. So if we have circular fringes, we can determine what the radius of curvature is. Now, this works well here if the radius of curvature is long. What if I want to measure a shorter radius of curvature? Now the fringes are going to get so close together I probably can't deal with them. So what would you do if you're measuring something with a shorter radius of curvature using Newton's rings? Yeah, you use another sphere. For some reason that gets all messed up on my computer when I do that. There, it's good. And so you would have another sphere. And so maybe I'll just write something on the board here. I mean, we have rho squared over 2r. And if we have two spheres, then we'd have rho squared over 2 times 1 over r1 minus 1 over r2. And if you want to go out to the mth fringe, that would be m lambda over 2. And so the 2's are canceling. And we could write this as just rho squared times delta r over r squared is m lambda. And we could write rho as, what do I say, d here is the diameter, so that could be what? D squared over 4 delta r over r squared is m lambda. And then we could just solve for delta r, and we get 4, just like I have on a screen here, 4m lambda r squared over d squared. And so as long as I know the radius of curvature here, I can of the reference surface, and I can determine delta r here. Now I wrote this here for really having circular fringes, but it doesn't have to be. I mean, I was thinking of circular fringes, but it could be just curved fringes like this, and I just see how much it curves, and so m is not necessarily an integer. It could be some fraction of a wave, and still put that in the equation. Okay. Okay. Any questions on that? So if you visit an optical fabrication facility where they make a lot of different optics, you'll see that they will have a lot of test plates of different radius of curvatures, and so they can easily do a test like this. So that was everything I wanted to say about measuring radius of curvature. And what I want to do now is to talk about measuring surface figure of these curved surfaces. And we're first going to start out with 2 or 3 techniques that you're all experts on, and then we'll go on to something that's new. But I mean, we've talked so much about using test plates to measure both flat surfaces and curved surfaces. And I don't know if there's anything really new to add here. It's just that, I mean, we know that the 2 surfaces have to be pretty close to the same shape, otherwise we'll get too many fringes to analyze. And so that's kind of one drawback. You do have to have all these different test plates at different radius of curvatures. And then the other drawback, when you think about the classical Fizeau and test plate, you're putting the 2 surfaces right next to each other, and it's very easy then to I mean, you would never do it, but some of your friends might scratch one of the surfaces. And then, you know, the next one that again you're experts on, so I don't need to say much here, is measurement using a LUPI or Twyman-Green interferometer to measure spherical surfaces. And I mean, the nice thing here is that once I get a nice setup here, I can measure almost any radius of curvature concave surface that I want. And remember the procedure for setting this up. Since we didn't have a lab with the course, maybe I'll go through it real fast here. You would first set this up and put a card here with a small hole in it, so the light goes through the card. And then you put the mirror out here and adjust that both longitudinally and tipping and tilting to make the light go back through the card, or the little hole in the card. And now if I look down here, I would see 2 spots, one from the reference and one from the test. And I would just tip and tilt to bring these 2 spots together. And if I look down here in the interferogram plane, then I will see the interference fringes, and they'll probably be curved. But then you just tweak the distance here a little bit to get straight fringes. So a concave is, you know, this is wonderful. Almost any radius of curvature, as long as your lab is big enough, I guess, to have the separation here. Convex is a different story. You'd put it in here, and so you just have a small range of radius of curvatures of convex surfaces that you could test. And of course, what we're really doing is testing the lens and the mirror together. And so if I want to test that lens, I just make sure I have a good mirror. And we're testing the lens. And another way to test the lens would be to put a flat right here at the focus. And why don't we want to do that? Why did we say that wasn't so good? Unless you're selling optics, it's good. Buying optics is not good. Yeah. Well, right. The beam here would be flipped over, going back. And so you'll never see coma. You never see the odd aberrations in this lens if you just put a flat there. So if I want to test a lens, I have to use either a concave mirror or a convex mirror. And I probably showed you that interferogram before. So the good features, I mean, I love the LUPI. I absolutely love it. Good features are that any size concave optics can be tested. All we have to do is make sure that the beam is diverging fast enough to fill the surface when it's placed so the center of curvature at the focus of this lens. So that's nice. The 2 paths in the interferometer do not have to be matched as long as we have coherence. If we use a single mode laser, single longitudinal mode laser, then this is wonderful. You don't have to worry about matching paths at all. And that's when the laser came along. That's when the Twyman-Green really became popular. And you're getting measurements just like you would with a test plate, except it's non-contact, so you don't have to worry about damaging the surface so much. Now the test is sensitive to vibration and turbulence, and it's a little more expensive because you typically have to have what, a good beam splitter, a good reference mirror, and a good diverger lens. Now at the end of this course, we're going to talk, I think it's the next to the last chapter in the course, we'll talk about absolute measurements. And we'll talk about a way of calibrating out these errors in the interferometer, which work pretty well. But generally you don't. Generally you really want to have good reference mirrors, beam splitters, and diverger lenses. So that makes it more expensive. And vibration, we've talked about special interferometers where you phase shifting, we take all the phase shift frames at once and take them real fast, and you cut down on the effects of vibration. And you average a lot of data frames to average out air turbulence. But if I'm just looking at fringes here, you know, the vibration really is bad. And there's a simple little thing you can do here that makes an enormous amount of difference. And you won't believe how much difference it makes unless you actually try it yourself. But say you have, you know, too much vibration here. If I just put something like a meter stick rest down here and back here, so I kind of couple the vibration. I mean, it's a very simple little thing, but it can make a tremendous amount of difference. It's almost unbelievable how much that can help. Of course, if this is several meters away, that's not going to be so practical. But if they're a meter or two away, you can just lay something on top here and couple the vibration, and it makes a lot of difference. So I guess those are the advantages and the disadvantages. And I guess I already have said, no, I didn't say this the first thing. You could mount the reference mirror on the surface being tested. This actually helps a lot too. So what I could do here, so this is what I'm testing. I could put a little mirror, fold mirror here, send the light out here, and mount another mirror right here. And so the light would go here, here, and back. And again, I'm kind of coupling. You know, if it's vibrating, the reference is vibrating too. And so I'm changing both test and reference. And that will cut down on the vibration. And that's really handy if this is a few meters away, so I can't do that little trick with my meter stick. Little fold mirror, reference mirror here, can make a lot of difference. Make the difference between being able to do a test and not being able to do a test. Okay, I guess that's it. And then the third interferometer that you've seen before, and but I'll mention it because it's so commonly used for testing the spherical surfaces, and that's the laser-based Fizeau interferometer. And so now the only good optics we have to have here is the last surface. Only real good optics. You don't want garbage back here, but only real good optics is the last surface. And this has become a very common way of testing both concave and convex surfaces here. And if this is, you typically will have an uncoated surface here. In a little bit we'll talk about the swim interferometer where they coat this surface, and we'll talk about the problems you get into with that. But if typically this is an uncoated surface, so you're getting like 4% back. If this is uncoated, that's great. If this is a 90% coating, then you put in your attenuator here, and so you cut down the light, so you get about 4% back. And that attenuator, why does that have to be thin? Why can't I just put a glass plate in here? Yeah, get aberration, get spherical aberration. One thing I hope you learn is you don't want spherical beams to go through glass plates because you pick up aberration. You want this to pick up spherical. If you tilt the plate, you get coma and astigmatism. Plain parallel plates can drive you crazy. But make this thin, a thin pellicle, and don't stick your finger through it, and this will work great. Or sometimes, often they just put the coating on this surface here, kind of an attenuating coating that will cut down on the amount of light coming out here. And then one more slide that you've seen before, and then we'll get to some new stuff, I think. I can't resist asking you whether this is a hill or a valley. And so the answer I'm hoping you're thinking is that just looking at that interferogram by itself, what is it I'm hoping you're thinking?
I have no idea.
Yeah, I have no idea. Very good, very good. That'd be a heck of an answer to a test question, wouldn't it? I have no idea what the answer is. But anyway, if you do something like push in on the mirror, and that makes the fringes go one way or the other, and let's say they go to the right, and so pushing on the mirror is like putting a big bump on the mirror, and so that little region there must be a bump or hill. So if I had, I set this up, and I have this pushing in, and the fringes move this way. If I tip and tilt this to change the sign of the tilt, two things are going to happen. This little bump here is going to move in the opposite direction, and when I push in on the mirror, the fringes are going to move in the opposite way. So everything, it just works out. Okay, so you're all experts on this. And I guess one last thing here is comments. The quality requirements in a diverger lens are less than for a LUPI or Twyman-Green because of this common path feature, the cost is less. Disadvantages, well, it's not as flexible. I mean, you have a path difference here, and there's no way of varying what that path difference is, and so you definitely have to have coherence length of the round trip path difference here. Well, if I went back to I could always tune the coherence requirements by moving this back and forth. And if I really were desperate, had a very short coherence length laser, this mirror could be moved back, or could be moved up here, and so this path was equal to that path. Probably don't want to do that, but I will if I have to. And some lasers, like a helium neon laser, if it's more than 10 centimeters long, you might have more than one longitudinal mode, and you can tune this, moving the mirror back and forth, so the round trip path difference is an even integer number of laser cavity lengths, and then you have good coherence. And so even with a fairly powerful helium neon laser with several longitudinal modes, if I can move this a distance equal to whatever the cavity length of the laser is, I can always tune this so the round trip path difference is always an even integer number of laser cavity lengths, and I'll have good contrast fringes. With a Fizeau, I'm stuck with whatever the path difference is, that's what it is. So it's not as flexible, not as light efficient. I should have showed that. First off, the light reflected off its beam splitter, I'm just throwing that away. I guess I could go to some polarization techniques to not reflect light. And then I'm getting, I'm limited to like 4% reflectivity here. And so if I have a lot of light coming back here, I have to attenuate that. So it's not a very light efficient interferometer. And the common path makes it more difficult to do some types of phase shifting, such as polarization techniques, although we did come up with a way of doing that that we showed earlier. But it's more difficult. But in spite of that, the laser-based Fizeau is used a lot more than a Twyman-Green. Okay, any questions? So one thing you might say, if I have a high reflectivity surface here, why do I put in an attenuator? Why not just put a high reflectivity coating here? And that takes us to our next topic, SWIM. Now, SWIM stands for Spherical Wave Multiple Beam Interferometer. And I have to admit, I don't quite know how that stands for that. But anyway, that's what the paper that's written on this, that's what they called it, SWIM. And what we're going to do here is going to be a Fizeau type interferometer. And we're going to use multiple beams. But we're going to run into a problem. Now, I'll tell you, I'll start right out from the beginning saying I think the SWIM is almost useless. But I want to talk about it because I want to talk about this walk-off problem. Now, I'm a little prejudiced in why I say the SWIM is useless. When I got out of college, I went to work for this company called iTech in Boston. And our major competitor was a company called PerkinElmer in Connecticut. And the iTech interferometer was the LUPI. Guess what the PerkinElmer interferometer was? It was the SWIM. So first off, I have to hate the SWIM, okay? But even if it was not what the competitors had, I still would hate the SWIM. And over the years, I mean, the SWIM lost out for sure. LUPI did better. But in the SWIM, so it's a spherical wave, multiple beam. So what they did, this looks a lot like the laser-based Fizeau interferometer. We have a laser here, light going in here. Here's our reference surface, and we have a lens, so the beam going through here is normal to this surface. And what they had then, I mean, this was a separate element with a spherical surface. And then here's the mirror they're testing. We're saying it's a concave mirror, and that really was what it was intended for. And what they did, they put a highly reflecting coating on here and a highly reflecting coating on here. And you've all seen Fabry-Perot fringes. And so you know the highly reflecting coating. And probably, maybe you've seen this with two flats next to each other. Have you ever looked at two flats, interference fringes, where both flats have highly reflective coating? You can see very sharp fringes. And so they thought, this is going to be great. This is going to give us very sharp fringes. And the problem with that iTech LUPI was that the fringes were sinusoidal, and this was in the days before phase shifting was around. And so you analyze interferograms by measuring the centers of the fringes. These are sinusoidal, a little hard to see where the center of the fringes would be. But here, we're going to use multiple beam, and so we're going to get very sharp fringes, and we'll be able to measure the center of the fringes much better than what iTech could do with a LUPI, and this will be a much better way of testing optics. Well, when they put this together, I'll come back to this slide in a second. When they put this together, they didn't see nice sharp fringes. They saw something that was not nearly as sharp, and it had ripples on one side. And the question is, why is this? And the problem is, well, if we're going to have several fringes, we have to have some tilt fringes. And so I'm going to have to tilt this mirror a little bit to get the tilt fringes. So this is tilted relative to the other one. But multiple beams, so the light's going back and forth here many times because of the high reflective coatings. But if this is tilted, the beam comes down here, this is tilted, it doesn't go right back on itself, it walks off a little bit. And then it's tilted, again, so it walks off more and more and more. So you get a lot of walk off. And the higher the reflectivity, the more reflections you're going to get back and forth here, and the more walk off you get. And so higher reflectivity, where normally with a Fabry-Perot interferometer, higher reflectivity, you get sharper fringes. It turns out with this interferometer, higher reflectivity made the fringes even worse. because of the Walkoff problem. And it turns out this had been studied way back a long time ago, 1953. So this was in the battle between the LUPI and the SWIM were in the late 60s, early 70s. But if you go back in the literature, there was a very nice Japanese paper that calculated just what the fringes would look like here. And lo and behold, the Walkoff does give you, really messes up the finesse of the fringes, and they're no longer sharp. So how can we get around that problem? Well, there was a guy by the name of Don Harriet, who actually worked at Bell Labs, but he was talking to someone at PerkinElmer, and he gave a solution. He said, you're getting this Walkoff here, but if I were to put a little lens right here in the center that imaged this surface onto this surface, so now the beam, it leaves at a different angle, but when it goes through that lens, it's going to be imaged back here, and the Walkoff's going to go away. So the whole point here, I want to make sure, the whole point of even talking about the SWIM, since I hate the SWIM, the whole point of talking about it is the fact that you get the problem with the Walkoff, putting in a lens here where you image one surface on the other, the Walkoff goes away, and the fringes become sharp again. Okay. So do you understand why that would work?
The whole advantage of this was pre-phase shifting, right?
It was pre-phase shifting. It was to get sharp fringes. So we're measuring the center position of the fringes, and we get the sharp fringes, and we could measure a fringe position better. That was the whole purpose of it. And but this Walkoff problem is something that I would say once every year or two I'll have someone contact me. I've set up this thing for multiple beam fringes and they're not sharp. What's the problem? And the problem is always that the two surfaces are quite a distance apart. You see the same thing with a flat. Let's say I have two flats, high reflectivity on both. Put them right next to each other. Oh, the fringes are really nice, nice and sharp. I separate them, and I get the Walkoff problem. So it's not just for optical testing, but people are, doing other things, trying to get multiple beam fringes. And if you have a separation between the two surfaces here, whether the flats or curves or whatever, you get the Walkoff problem. And at least if you have spherical surfaces where the light's coming to focus here, you can just put in a lens here to image one on the other. Now that lens, it doesn't have to do a great job of imaging it. Say it doesn't image the surface right here, but it images it a little bit distance away. Well, it's like having a cavity without much separation between it. And if you go through the analysis, the problem you get into here, the problem depends upon the reflectivity, because that determines how many multiple beams you have, and the problem depends upon the separation between the two mirrors. And if a separation is small, then this problem goes away. And so if I put in a lens here, but it doesn't do a great job of imaging that over here, it's still going to greatly reduce the bad effects, and my fringes have become much sharper. But there is one problem you can get into putting that lens in there. Can anyone think of another problem you might get into? Kind of a practical problem? What? The error on the lens. What's that? If it's not clean? Is that what you say? Yeah, well, it has to be clean. The lens doesn't have to be high quality. We're using a very small part of the lens, but it has to be clean, and it has to have an anti-reflection coating on it. Because, to get multiple beam reflections, what you're depending upon is a lot of beams reflecting back and forth here to get the high finesse fringes. That's why you have a high reflectivity. But if I have another loss in the system, like reflections from a lens in here, that's going to reduce the finesse of the fringes. And so the quality of the lens here doesn't have to be fantastic. It has to be clean. It has to have a very good anti-reflection coating on it. So, the problems with this is that both surfaces have to be coated. And so if you're fabricating optics, you don't want to have to coat the surface every time you test it. Not very practical. But this had to be coated. Had to put a lens in here. I mean, that was a nice, clever idea of Don Harriet to point out that if you put a lens in there, the problem goes away. And you have a fixed path difference. You need a long coherence length because I'm going to have all these multiple reflections. And so you have to have a single longitudinal mode laser, which is not a problem nowadays. It was more of a problem back when the SWIM was used. So this paper here, which I've read more than once, I guess, it's kind of a nice paper. It's written a long time ago. And I mean, to do these calculations, it took them hours and hours and days, because the computer they had in 1953. So I had a student called John Rogers, who I was very interested in this. And so I asked John to analyze this and hired him to do that. And I don't know, somehow nothing happened. And so I fired him, okay? I couldn't see anything happening. Well, a year or two later, he appears in my office where he's now completed his study. Even though he was fired, he continued to work on it. And he wrote what I thought was a beautiful paper in JOSA here. And so not only did he do calculations here, but he did some measurements using at that point we're just getting solid state detector arrays. And so he did some measurements here. And he had, I'm just showing one result here, but he had just beautiful comparisons between theory and measurements. And so this was for a particular case of reflectivity, 98.4%. The fringe spacing had to do with the tilt, how much tilt you had, and so that was important. And then the separation between the two mirrors of 4 millimeters was very important. So anyway, that's a neat paper. So I was just thinking yesterday when I was looking over these notes. So this paper in 1953, at the time when I first read this paper, which was something like 1982, I thought, boy, is that an old paper. It was 30 years old. Now this new paper here, this new paper is now 30 years old. So the other thing I think was kind of interesting, when I went back, the thing about this, I mean, to do these calculations were so difficult because of the computers. And so slow. But in 1982, I thought we had wonderful computers, Now 30 years later, I think the truth of the matter, my iPhone probably is a more powerful computer than what John did these results with. So 30 years from now, you'll have the same feelings about whatever the latest and greatest is. Anyway, I thought this was great. Even though I fired him, he kept working on it, and he did a wonderful job on this paper. Okay, so that's the SWIM. I don't like the SWIM, but I think the walk-off problem, you may see that a few times in your life, and it's nice to kind of understand a little bit about it. The next one we'll talk about here, let's see, the Shack Cube Interferometer. Okay, so this is one of Roland's ideas, and it's a Fizeau type interferometer. So we start off with a laser here, and this is going to have to be a single longitudinal mode laser because we have no way of adjusting path differences. They are what they are, and so we have to have good coherence. And typically what we have here is a cube beam splitter with a lens fastened or cemented on one side. And the light here from the laser, typically we focus it on the first surface of this cube, and we put a pinhole there to clean up the beam. So there's a pinhole mounted right on the, I'll show you a picture of one of these interferometers in a minute. Pinhole here, and the light's focused right on that pinhole, and that cleans it up. So here's our beam splitter. And the light goes out here. Now this is normally used just to test concave surfaces. If we want to test a convex surface, where we have to add some other optics. But so we put a mirror out here, where the center of curvature is back here where this light was focused. So that's on this surface, which is also on the last surface here too. And we're very clever when we put this lens on here. So we put a plano convex lens and cement that on the surface. And we want one where the radius of curvature, or the center of the curvature for this surface, is also at the other side of the cube. So this beam comes out here, and it's going to be normal to this surface. Going to be reflected right back on itself. So that will serve as the reference, and this is our test. So it's a regular Fizeau, and I should also say, so here we have maybe an eyepiece. The picture I show has an eyepiece here, but nowadays I'd probably put a CCD out here, and I wouldn't look at this through an eyepiece, but put a CCD and look at it probably on my computer screen. Now, you're going to have these two focus spots here, one from the reflection from the reference and one from the test, right back here. And so I can look right at this surface right here and see the two focus spots, and tip and tilt this mirror and move it back and forth and stuff to make sure that the two spots are on top of one another. So this assembly here is put on an XYZ stage, and we're going to adjust it then. So again, so this center of curvature here, or this focus is at the center of curvature of this mirror. So any questions on the schematic? So Schack actually, I don't know when he invented this, probably in the 60s sometime. And but Schack was never one to publish. Probably no one here has met Roland Schack, I guess, have you? Because he retired before you came. But he was so smart, and but he just didn't publish things, and he would write up something, and not write it up. He would put a few words down and some equations, put it on a piece of paper, and put the piece of paper in his file cabinet. And then 5 years later, some student would come up with a great new idea, and he'd go see Schack, and Schack said, "Oh yeah, I did that 5 years ago," and he'll go to his file cabinet, show you not only did he have the same idea, 5 years ago, he had the same idea you have now, but he probably understood it far better than what you did. Anyway, so the Schack cube interferometer is sort of like that. So after I came out here, I had George Hopkins working for me, and I said, you guys have to publish something on the Schack cube interferometer. And so I supported them to build a Schack cube interferometer, and then they published it. And I don't know how well we can see this. This is still around here someplace. So this is our XYZ stage. Oops. And laser coming around here, and microscope objective focusing the light on the pinhole that's on the cube. And then the light to the mirror would go out into the screen that you're looking at, and come back here, and here are the eyepieces that you would use to look at the interference fringes. And so that's a pretty compact, little, inexpensive little interferometer. And so what is good about it? Well, you only have to have one good surface. I mean, that's the same as with the laser-based Fizeau. I mean, this is very similar to the laser-based Fizeau, but much less expensive. Maybe not as versatile, but much less expensive. So you have to have a single longitudinal mode laser. If you want to test lenses or convex surfaces, you have to add some other lenses to the system. This is really intended for testing concave surfaces. You know, if you're testing a coated surface, well, you have to have, just like for the laser-based Fizeau, you have to have some type of absorber, something to attenuator, such as a pellicle. The beauty of this really, and why a number of these were made, and there used to be a couple of 3 companies that sold these, and maybe they still do, I don't know, but it's lower cost. Used to be you could buy an interferometer like this for $3,000–4,000. But it's not nearly as flexible as a Twyman-Green or a regular laser-based Fizeau. But for a small optic shop, it's a handy interferometer to have. And how could I phase shift this? Any ideas how I might phase shift it? I mean, Shaq, thought of this before the days of phase shifting, but been a few of these interferometers sold doing phase shifting. Well, the most common way is a PZT that moves this whole cube here a little bit, or moves the whole interferometer really a little bit to change this distance. It's not a great phase shifting, but it works okay. There's another practical problem. I remember George came up with this problem. You know, you start off with a cube beam splitter, and probably it has AR coatings on the side. Probably, maybe not very good AR coatings, but it has some AR coatings on the side. And you have a lens here. Well, you don't want that lens to have an AR coating. Certainly not on that surface here, because you're relying upon the reflectivity from that. So probably the lens you use doesn't have an AR coating, but the cube does. And so what you do is you cement this lens onto the cube. And when you put the cement there, that nice AR coating becomes a nice, highly reflective coating. And so before doing that, if you have an AR coating on the cube, you have to strip the AR coating off, because you don't want a reflection coming from the interface between the lens that you cement on and the cube. So any questions on the Shack Cube interferometer? Has anyone here used one? Because there's probably more than one around, but at least one around. It has not been used too much, and it's mostly, small shops that didn't think they could afford a more expensive interferometer would use this. And as I said, it has been used with phase shifting, but normally it hasn't. It doesn't use phase shifting. Normally, just look at the fringes. Okay, now we're finally coming to what might be my favorite topic for the whole course here. The Scatterplate Interferometer. Has anyone here used a Scatterplate Interferometer? Did you have that in any of the other classes? No. And I give a lot of short courses all around the world each year, and I always talk about the Scatterplate Interferometer because I absolutely love it, although I normally say about 10% of what I'm going to say to this class about it. And I'm lucky if I find one person in the world who's ever heard of a Scatterplate interferometer. All my short courses I give each year, if I have one person who's heard about it before, it's generally someone who went through school here at some point, heard about it here. It's not widely known. It's not widely used. And I don't know where you could buy one. You have to make one. But it is an incredible device. It is just, to me, it's just absolutely amazing that it works. And not only does it work, it works very well. And the nice thing here is it's not going to require any high-quality optics, not even a high-quality reference mirror. You can't. come up with many interferometers, you can say that about it. It requires no high quality optics. It's going to be common path. Test and reference beams are going to go essentially the same path. And because of that, it's going to be less sensitive to vibration. So, you know, if I try to set up a Twyman-Green on this table here in front of the class, the fringes would jump around like crazy. But I could easily set up a Scatterplate Interferometer here, and the fringes would be nice and steady. It would work very well here. It's a little bit less sensitive to air turbulence because of the common path. I mean, it's not perfect. You still can see air turbulence, but a little less sensitive. Just like I said, you didn't need any high quality optics. The light source can be almost anything. It could be a laser. It could be a mercury source, a sodium source, a 60-watt light bulb, a flashlight, almost anything. Doesn't require spatial coherence. Well, we'll talk about how much spatial coherence we need in a little while. It doesn't require much temporal coherence. We'll talk about that also. It can be almost anything. It's amazing. The scatter plate, that's going to be the critical component, and we'll talk about it. We'll talk about why it has to have inversion symmetry. And we'll even talk about how you can make one of these. And it's fantastic. So let's go on. And first I'll say it was invented by a man by the name of Jim Birch in England. And as we go through this, I'll show his paper that he published on this. And it's just so clever. Okay, so here I'm going to show it for testing a concave mirror. You can use it for testing other things, but the concave mirror is what it's best for. If I test convex or flats or something, I'm going to have to add some lenses in here, and then these lenses are going to have to be high quality, and some of the great features of the scatter plate go away. And so I really want to use it for testing concave mirrors. And I should also say I love this interferometer so much. I've had 2 students do their PhD dissertations on it, and we'll talk a little bit about what they did as we go through this. Okay, so we start out here with source, and as I said, that can be anything, almost. And then we have this lousy lens. It doesn't have to be good at all. And then a crummy beam splitter. And then we go through this scatter plate. And I'll come back to that in a minute. That's the tricky thing, I guess I'll say. And the light here goes to the mirror and comes back through this lousy beam splitter, and we have another crummy lens here and our interferogram back here. So this first lens, what it does, it's going to image the source onto the mirror being tested. And it doesn't have to be a great image at all. We'll worry about that in a little bit, but it doesn't have to be a very great image. And then this lens here will image this mirror that we're testing back here where we're going to see the interference pattern. And since the source was imaged here, the source is also going to be imaged back there. Now, if I think for a second here, the light comes along here, and this scatter plate, and if I brought one to class, I mean, it would look like a piece of ground glass, unless you looked at it through a microscope. Just looking at it, you say, oh, well, okay, a piece of ground glass. And so when the light strikes this, I mean, 2 things can happen to the light. It can be scattered, or some of it will go directly through. And so we have a scattered beam, and we'll have what I'll call an unscattered or a direct beam. And I didn't say it before, but the scatter plate is going to be put near the center of curvature of this mirror. And we'll see later what happens as I move the scatter plate around. So anyway, we have 2 beams coming here, a scattered beam and a direct beam. And this lens is imaging the source here, so the direct beam is going to be imaged here. The scattered beam, oh, that's going to be imaged all over the place. I mean, it's going to go all over the place here. And some of it's going to strike the mirror, some of it's going to go by the mirror even. But scattered light will strike here. And it's going to come, the mirror is going to send it back in this direction. So when the light comes back through the scatter plate the second time, two things can happen to it. It can be scattered or it won't be scattered. And so I'll get scattered light and unscattered light coming back. And so I really have four beams here. I have a beam that was scattered the first time and scattered the second time. I will have a beam that was scattered the first time and then went directly through the second time. I'll have a beam that went directly through the first time and was scattered the second time. Then I'm going to have a beam that wasn't scattered either time. It's going to be direct. So in this space over here, I have these four beams. Now I like two beam interference. I don't like four beam interference. So I want to argue why I can forget about two of these beams. And I should say a lot of my description here is going to be a lot of hand waving, trying to explain what happens. But the first student I had do a PhD on this, his name was Larry Rubin. I mean, he went through all the math of this. And his dissertation was pretty thick, filled with equations. And so all my hand waving here, I'll back it up with Larry's equations if you want to see them. But I should warn you, Larry went through here, he was a great student, he went through here and got his PhD doing this. And the first thing he did was to give up optics. And somehow, I don't know, I thought the Scatterplate Interferometer, I always thought it did something to him, I don't know. He gave up optics and he began playing the fiddle in bars in Texas and New Mexico, and he was making no money, and he was out sleeping in the desert at night. No, it was horrible. I thought, what have I done to this guy? Anyway, after a year or so of that, he came back, and he's had a very good career in optics. Unfortunately, he passed away about a year ago, but he had a very good career. So he recovered from the Scatterplate Interferometer. So I don't want to go through all the equations here because it might do that to both you and me. I don't know. Anyway, we have these four beams, and I want to get rid of two of them because I don't like four beam interference. So the first one, I don't like this scattered beam because, the light is scattered here, and then it comes back, it's scattered again. It's just going to be a mess here. And what it really does, it's going to reduce the contrast of the fringes a little bit. But I'll show you some interference fringes in a while, and you'll see that it doesn't reduce the contrast very much. And so I'm going to forget about the scattered beam. The other beam I want to forget about is the direct. So the light comes here, and the direct beam is focused right there. And then when it goes directly through here, it's going to be focused right there. And so what it's going to give you is a bright spot, or in the literature they refer to it as a hot spot. And when I show you the final interferogram, you're going to see a real bright spot, but it's localized. And so, the interferogram's big, there's a little bright spot in it, I'm going to forget about it. So direct beam, I've forgotten about it. The scattered direct beam, that's going to turn out to be the test beam. So the light is scattered here, and it's going to cover this entire surface, okay? And so any height variations, any errors in this surface, height variations, that's going to affect the scattered light when it's reflected off of here. And it's going to turn out that it's going to, this test beam, when I interfere with my reference beam, it's going to give me an interferogram just like I would get with a Twyman-Green or a Fizeau, except for this hot spot. And in fact, I have some background scattered light, which reduces the contrast a little bit. So this is going to be my test beam. Now my direct scattered beam will be the reference, because if you think here for a second, the light is coming to focus right there. And any errors in this surface, it doesn't see. It's just seeing a little bit of the mirror. and it will come back here and be scattered a second time. So it does not see any of the errors in the mirror, and so that will be my reference beam. And so back here, the interference of what I'm calling test beam, scattered direct beam, and the direct scattered beam will give me an interferogram that's going to be just essentially the same as what I would get with a Twyman-Green or a Fizeau type interferometer. And it's what I'll call a common path interferometer, in that both the reference beam and the test beam travels the same distance here, and both are reflected off this mirror. So if this mirror, if I have a little vibration causing it to move back and forth, it's doing this essentially the same thing to both the test and the reference. Now, if this vibration causes this to tip a little bit, well, that's a little bit different due to the test and reference. But the biggest component of vibration will just be a longitudinal here. And so that's why this system will work very well, even if I just set it up on a table like this or a desk like what you have. Now, you know what? When I first look at this, I would say there's no way in the world how this interferometer can work. And why do I say that? Well, I'm trying to measure errors in this mirror by looking at little phase changes I get. I have a scattered beam, coming out to the mirror, and the distance that beam has to travel depends upon the little height variations on the mirror. And so I'm trying to measure little phase variations in this scattered beam due to height variations on this mirror. But at the same time, when this beam is scattered, you get all kinds of phase changes. So how can I pick out little phase changes due to path differences here resulting from height variations on this mirror from all of the phase changes due to the light being scattered here? So somehow it doesn't seem like this would work. Yet it does work. And it works extremely well. And what I'm going to do is to stop at this point, and the next class will start up by talking about why it does work. Now, as I said at the beginning of class, unfortunately next Tuesday I will be in Chicago, probably freezing to death in Chicago. And so I won't be here on Tuesday. So first off, you don't have to hand in your homework until Thursday of next week. So I'm sure that, if you really want to hand it in early, you could put it in my mailbox, but you don't have to. Next Tuesday's class, I'm going to record that tomorrow morning at 11 o'clock in the room next door. And any of you who want to come can. And we're going to talk a lot more about the scatterplate interferometer, describe just how it works here. I have so many details, so many things about the scatterplate that I just absolutely love that I can't wait till the next class to talk about it. So I'll see some of you tomorrow, and the rest of you